Welcome to the Deep Dive. Today, we are undertaking, I think, a really critical mission. We're trying to understand how to bridge this gap between a general AI that's, interesting to play with and one that has truly intelligent, verifiable expertise.
That is the core challenge, isn't it? I mean, these general large language models, they're phenomenal at language, at inference,
Yeah.
but they're fundamentally boxed in by two things.
Okay.
First, the knowledge cutoff date of their training data, which everyone talks about. And second, their total, and I mean total ignorance of anything specialized, private, or happening in real time.
Right. So if I ask a general model about my company's Q3 budget,
It's going to guess. Or, even worse, it's going to hallucinate. It'll invent a number that sounds plausible, and that's the danger. Ask it about a new law that was just signed, same problem.
exactly. So what we're talking about today is moving past this sort of smart guessing and getting to reliable, fact-based analysis. We need AI agents that can actually be genuine experts.
Yes.
The kind that can read thousands of pages of really dense, specialized knowledge, pull out factual evidence, and never, ever make things up.
And that expertise, that ability to handle these huge specialized data sets, whether we're talking about dense legal documents, textbooks, proprietary company PDFs, complex case laws, or internal SOPs, it's all delivered through one specific piece of technology.
And that is Retrieval-Augmented Generation.
RG. That's the one.
So our mission today is to do a masterclass in RAG implementation. We're going to pull the vital steps, the specific tools, the best practices, everything, directly from our source material. That's Mr. Zahir Ahmad Mir's work in AI Agent Makers. And we're going to show you, the listener, exactly how to build a grounded, knowledgeable agent.
And importantly, often using tools that are completely free and accessible. This isn't some far-off enterprise-only concept anymore.
This is the real pathway to creating what? The corporate historian,
Yeah.
the automated legal analyst.
The medical research assistant, yeah. And it all starts with just accepting a simple truth about where AI is right now.
Okay, so let's unpack that a little bit. This need for external knowledge. If an LLM is trained on, trillions of tokens from the internet, why isn't that enough? Why does it need RGA?
Well, because the nature of intelligence, especially in any professional context, it isn't just a function of sheer model size or how many parameters it has. It's a function of access.
Access to external, verifiable, and up-to-date knowledge.
Up-to-date is the key word. The LLM might know a million general facts about the world from its training run 2 years ago, but it has absolutely zero insight into your specific client history, or the unique definitions buried in a legal contract you signed last month, or a scientific paper that was just published this morning.
So RGI basically acts as the agent's research librarian. It's the thing that plugs it into these massive, specialized libraries that exist outside of its initial brain.
A librarian is the perfect analogy, and by doing that, it grants capabilities that were they were impossible for LLMs working in isolation before.
We're talking about allowing an agent to, quote, read the equivalent of hundreds of full books.
And not just read them, but retrieve only the hyper-relevant little parts needed for a specific question, answer with factual evidence, and, this is the most important part, stay grounded while providing those all-important citations.
This is what fundamentally changes the utility of AI. It transforms it from a general-purpose conversation partner into a factual, accountable analyst.
A tool you can actually trust with high-stakes work.
So with the why firmly established, let's now look at the mechanics. How is this knowledge system actually built? Let's define the core concept, array itself. What is this simple but really elegant formula that defines the whole architecture?
Right, so a RAG is, you could think of it as a two-part harmony. It's an elegant little equation that leverages the strengths of two totally distinct systems. The formula is just RA equals retrieval plus generation.
Simple as that. Okay, walk us through the first, and I argue maybe the most important, half of that equation. Retrieval.
Retrieval is the smart search engine part of the system. So when you ask the agent a question, the agent absolutely does not try to send the entire library, the 500-page manual, the 10,000 case laws, over to the LLM.
Because that would be impossible. You'd hit the context window limit instantly.
Instantly, and it would be incredibly slow, and it would cost a fortune in processing tokens. So instead, the retrieval component intelligently searches a specialized knowledge store, which we call a vector database, to find only the handful of text fragments, we call them chunks, that are mathematically the most relevant to your question.
Just the top few results.
Just the top few?
And then generation is the synthesis stage. This is where the intelligence of the LLM, your ChatGPT, your Llama, your Claude, finally comes into play.
That's right. The LLM receives two things: the user's original question, plus those retrieved tiny, highly targeted text chunks, and then it's placed under very strict instructions through what we call a system prompt.
And the main instruction is,
Generate an answer only based on the information I've just given you in these chunks. This whole process, this combination, is what gives an AI agent its true memory and its domain intelligence.
it's the difference between asking an open-ended question to someone who's read everything in the world but has no immediate access to their notes, versus asking a practicing expert who has just had the 3 most relevant pages from their entire library highlighted and placed right in front of them.
That is a perfect way to put it. It's the operational framework that allows AI to function reliably in the real world, not just in a chat window.
Okay, this is where it becomes absolutely essential for anyone listening to really grasp the value proposition. Why does RAG matter so much? We all know that general LLMs have these critical systemic flaws. Our RAG is designed specifically to address these pain points.
It really is. It turns them from, academic curiosities into enterprise-ready, reliable tools.
So what's flaw number 1 that it fixes?
The big one, the infamous problem of hallucination. Because the LLM is restricted entirely to the facts you just retrieved for it, you virtually eliminate its ability to confidently invent things or speculate.
And in a business environment, a model just making up a financial figure.
It's catastrophic. It's a non-starter. RI acts as that verifiable constraint. It's the safety rail.
Okay, and then there's the problem of temporal relevance, the outdated information issue.
Yeah, if you rely on a general LLM that was trained up to, say, 2023, it knows nothing about the new corporate policies you rolled out in 2024. With RAG, you just update your knowledge store. You drop the new documents in.
And instantly the agent is up to date.
Instantly. It completely bypasses the LLM's fixed training cutoff date. It provides this grounding in the here and now.
This speaks directly to reliability and accountability. I mean, without RAG, the answers you get are often just unverified. You can't trace them back.
Right. General LLMs provide unreliable answers, and crucially for any professional setting, they lack traceable citations. With RAG, the agent is generating answers that are derived directly from a source you provided, your case law, your proprietary manual.
Which means it can cite its sources.
It means the agent can provide authentic references and is therefore accountable and auditable. You can check its work.
And finally, there's a purely technical constraint that RAG cleverly bypasses: the limited context window.
And this is a physical architectural limitation of the models themselves. Without RAG, even the biggest models can only ingest maybe a few dozen pages of text in one go.
Yeah.
That makes any kind of duck research impossible.
But by using that retrieval mechanism, that super efficient search,
You can effectively analyze gigabytes, even terabytes of data. It doesn't matter how big the library is because you're only ever looking at a few relevant paragraphs at a time.
So with RAG, we can analyze these massive collections of financial files, legal history, scientific studies, all while maintaining crucial organizational memory across years of data. This is what allows an agent to perform complex, fact-based research tasks that would be absolutely impossible for an unaugmented general purpose LLM.
So what, for any developer or business leader listening, is crystal clear? RAR is the architecture that enables true enterprise functionality. It's what turns an expensive general model into a reliable, domain-specific asset you can build a business on.
That distinction is just paramount. Now that we understand what R is and why it matters so much, let's get into the engine room. If you're going to build this system, you need to understand the fundamental mechanics. So let's do a deep dive into the 4-step R pipeline.
Okay, this is where the concept becomes construction. The entire success of a RAG system, and I can't stress this enough, it all hinges on meticulously preparing your specialized knowledge data. And that preparation begins with step 1, chunking.
Chunking. It sounds so mundane, but if you get this wrong, the entire RAG pipeline just fails, right? The search engine can't work efficiently.
It fails spectacularly, absolutely. So think of your source document, a 300-page book, or a technical manual. It cannot be stored whole in the vector database. It has to be broken down into small, digestible pieces. We call these pieces chunks.
And the source material suggests a pretty specific ideal size range.
It does, around 200 to 500 words each.
And why that specific range? What's the thinking there?
Well, it's really a balancing act. If your chunks are too large, say 1,000 words or more, when the agent retrieves one, it pulls along way too much irrelevant information. It's like asking for a specific recipe and getting the whole cookbook. The LLM struggles to find the precise answer and can get confused.
Okay, and if they're too small?
If they're too small, say 50 words, you strip away all the surrounding context that's necessary to understand the main idea. You get these fragmented, almost meaningless results. So 200 to 500 words seems to be the sweet spot. It ensures you have a solid, self-contained unit of context.
And then there's this detail that often separates an amateur implementation from a professional one: the necessity of overlap. Can you explain why we absolutely need overlap between these chunks?
Overlap is a subtle but completely vital detail for maintaining continuity. It's critical for preventing what we call context drift.
Context drift. Okay.
Yeah, imagine a really crucial, complex idea is explained across two sentences. Sentence A ends chunk 1 and sentence B starts chunk 2. If there's no overlap between those chunks, the agent searches, finds chunk 1, but the context needed to complete the thought sentence B is lost. It lives only in the next chunk, which wasn't retrieved.
So the search algorithm only sees half the argument. It's missing the critical conclusion.
Exactly. But by overlapping the chunks, for example, making the first, say, 10–20% of chunk B a direct repeat of the end of chunk A, we ensure that if a search query lands near that boundary, the retrieval is guaranteed to pull in sufficient surrounding text from the previous section.
It stitches the context back together.
It prevents that context from being broken or lost at the boundary, ensuring you get these hyper-precise and connected search results.
Okay, so once we have our perfectly sized overlapping chunks, we move to step 2, embeddings. This is the process that allows a computer to understand the meaning of the text, not just the keywords inside it.
This is where we translate human language into pure mathematics. An embedding is the process of converting each of those text chunks into a vector.
And a vector, for anyone who's not deep in the math, is just a big list of numbers, right?
That's all it is. A massive array of numbers that serves as a numerical representation of that chunk's underlying semantic meaning. Specialized models do this conversion, and these vectors are then mapped as points in a high-dimensional space.
We're literally moving the concept of a sentence into a point on a graph.
Precisely. And the key insight, the real magic, is that the closer two vectors are in this multidimensional space, the more similar their meaning is. And that's true regardless of the exact keywords they happen to share. This is the core mechanism that enables conceptual search rather than that old, clunky keyword matching search from the past.
So what tools are developers actually using to create these embeddings?
Well, the landscape is rich, which is great. You have fully free and highly accessible options like sentence transformers, which is widely used for easy integration. Then you have commercial options like OpenAI embeddings. And then there's this growing world of sophisticated open source options like Hugging Face embeddings and Llama embeddings.
And the choice there comes down to what? Cost, speed.
It's usually a balance of cost, speed, and whether the model is specifically trained for your domain, which, as we'll discuss later, is a really key best practice.
Okay, so now we have a massive database, but it's full of these numerical vectors, each point representing a piece of our knowledge. How does the agent find the exact information it needs among potentially billions of these vectors? That brings us to step 3, vector search.
Right. So when you, the user, asks a question, the query itself is immediately translated into its own vector using the exact same embedding model we used on the documents.
So now you have 2 sets of vectors to compare.
You have the stored knowledge vectors in your database, and you have this one new query vector. The agent then performs what's called a similarity search.
And how does the system mathematically figure out which vectors are closest? I think we need to understand the mechanism there.
Yeah, the most common mathematical method is called cosine similarity. It sounds complex, but the concept is pretty intuitive. Imagine your query vector and all the knowledge vectors are arrows pointing in different directions in that high-dimensional space. Cosine similarity just measures the angle between those arrows.
So if the arrows are pointing in almost the same direction,
the angle is very small, and it means the meanings are highly similar. If the angle is wide, the meanings are distant. It's a computationally brilliant breakthrough that makes this kind of conceptual search incredibly fast and effective, even over billions of items.
So the agent just calculates the cosine similarity for every vector in the database, ranks them from most similar to least, and retrieves the top performing ones.
Exactly. The output of this entire step is the retrieval of, typically the top 3 to 10 most relevant passages. And these retrieved chunks, and only these chunks, are what the agent will pass forward to the next stage.
And there are specialized tools for this part of the job.
Oh yeah, you need them. The source material highlights a few great ones: the lightning fast and free face, the super easy to use and also free chroma, and then the enterprise heavyweights like Weaviate and Milvus.
Which naturally leads us to the final act, step 4, grounded answer generation. This is the final synthesis stage.
This is where it all comes together. The retrieved chunks are packaged up, along with their source metadata, and they're sent to the LLM alongside the user's initial question. But, crucially, the system prompt has to be perfectly aligned to enforce that grounding we talked about.
The core instruction has to be crystal clear.
It has to be something like, generate an answer only based on the provided data, nothing else.
And if the LLM tries to speculate or, pull in some of its general outside knowledge, that prompt acts as the ultimate constraint.
It does, and the result is a powerful, reliable answer complete with references that is guaranteed to be grounded in your data. This integrity and trustworthiness is the entire value proposition of RAG. This whole 4-step process, chunking, embedding, vector search, and generation, that's the pipeline that transforms raw, messy data into an intelligent, functioning knowledge system.
Now that we understand the process, let's turn to the toolkit itself. For anyone out there looking to actually implement RAG, the choice of the vector database is probably the first major architectural decision you have to make. So let's look at the specific options for vector search, starting with the accessible, free solutions.
Right, and when you're building your first agent or just, testing a concept, the two standouts are definitely Face and ChromaDB, and they represent two really different design philosophies.
Okay, tell us about FaceS first. That's Facebook AI Similarity Search.
Yeah.
It's known for being incredibly fast, but what's the trade-off?
FAS is brutally efficient. I mean, it is often cited as the fastest vector search solution available, period. It was developed by Meta, Facebook, and it's been optimized for search speed over massive static data sets. It's 100% free, open source, and it's used heavily in big production systems.
But the trade-off is complexity.
It's complexity. It's best suited for developers and experts who are comfortable managing the indexing process themselves and who really prioritize latency above all else, especially when you're dealing with very, very large collections of data.
Okay, and then we have the other option, ChromaDB, which seems to prioritize ease of use.
Correct. ChromaDB is the ideal entry point for beginners. It's also fully free, but it's designed from the ground up to be user-friendly. It has excellent Python integration. It's easy to get running. If you are building your first educational RAG agent or a small to medium internal knowledge base, Chroma is absolutely the recommended starting point. It offers a great balance between features and ease of setup.
So then moving into the enterprise world, scale becomes the defining factor. What advantages do tools like Weaviate and Milvus offer that would justify moving beyond those free options?
It really comes down to scalability and advanced features. Weaviate is extremely popular in that space because it offers a great user interface and really strong indexing performance. But crucially, it offers true multimodal support.
Meaning it can handle more than just text.
Exactly. It can natively handle vectors derived from text, images, audio, other data types, and it integrates seamlessly with R-Gray frameworks like LangChain. So if your knowledge base needs to include, say, pictures of machinery or technical schematics alongside the text manuals, Weaviate is a very strong contender.
And then there's Milvus, for the truly enormous scale. When do we absolutely need the Milvus powerhouse?
You reach for Milvus when you're operating at petabyte scale. If you're a multinational corporation, a major research institution dealing with billions of documents, Milvus offers horizontal scalability and resilience in demanding environments that the smaller databases just can't match. It's built for things like reliability, disaster recovery, and handling continuous, extremely high-volume querying and data ingestion.
That gives our listeners a really clear decision matrix for their knowledge base infrastructure. But the source material also mentions a specific user-friendly tool, Google's Notebook LM, that offers a clever shortcut into a sort of hybrid ORGAE approach.
Yeah, Notebook LM is essentially a consumer-friendly interface for this idea of grounded knowledge retrieval. It's a tool that allows you to just upload PDFs and books very easily, and it automatically creates summaries and flashcards based only on that material you uploaded.
So how do we use that in a RGRAG context? It's not a full system.
It's not. The suggestion is to use Notebook LM alongside a generative tool like ChatGPT. You're using Notebook LM for the easy organization, the data ingestion, and the grounding. And then you're using the pure generative power of a large commercial LLM to query and analyze that knowledge base you built. It's a great way for a non-developer to start experimenting with the core concept of grounded intelligence right away.
It democratizes the capability, really. Okay, let's move on and see the RAG pipeline in action with some specific high-value real-world applications. This is where we see the concept really transforming industries. And let's start with a really complex domain, the legal RAG agent.
The legal domain is a perfect fit for RAG because in law, accuracy isn't a suggestion, it's an absolute requirement. You need verifiable fidelity to specific texts, case laws, statutes, precedents. The toolkit here is often a combination of Paddle OCR, AACS, and ChatGPT.
Okay, so we know ARSS handles the speed, ChatGPT does the generation. Why is Paddle OCR so necessary for legal workflows specifically?
This is a great point about data hygiene, which is so important. A lot of critical legal history. We're talking older case laws, historical briefs, archival contracts. It exists as poor quality scans or images from microfiche or PDFs that were generated with weird, archaic fonts.
And standard OCR tools just can't read that stuff.
They fail spectacularly. They introduce all kinds of errors and noise. Paddle OCR is an advanced, robust OCR tool that excels at handling those low-quality, image-based documents. It cleans and converts the text reliably before we even get to the chunking and embedding process. Without that reliable OCR, your legal knowledge base would be riddled with errors and functionally useless from the start.
So once those raw legal documents are cleaned up and vectorized in FACE, what happens when a legal researcher asks a really challenging question?
Well, the agent retrieves the most relevant paragraphs of precedent, but the key is the output it generates. The agent moves way beyond a simple summary. It can generate specific legal arguments, it can analyze contradictions between different legal findings, synthesize precedent summaries, and crucially, it can write the ratio decidendi,
The binding rule of law.
the binding rule of law on which a judicial decision is based, with a direct citation back to the original case file. This is advanced legal reasoning support. It moves far, far beyond simple information retrieval.
That is absolutely moving into expert territory. Okay, let's switch gears to the educational RAG agent. This presents a different set of challenges, specifically around all the varied content sources you find in education.
Right. This scenario often uses ChromaDB for its ease of management, combined with Whisper and ChatGPT. Educational environments need robust, easy-to-manage knowledge bases that students can really trust.
And the workflow here is fascinating because it incorporates not just textbooks, but also lectures via Whisper. How does that integration actually work?
This is a phenomenal example of multimodal integration. Educational resources are rarely just textbooks, are they? They include recorded lectures, instructor commentary, video lessons. Whisper, the powerful speech-to-text tool, is used to convert all those lectures into written transcripts before the vector store is ever created.
So the knowledge base contains not just the static textbook content,
But also the instructor's spoken context, their specific explanations, their off-the-cuff examples,
The-
all of it.
So a student isn't limited to just querying the text. They could ask something like, can you explain the Coriolis effect using the example Professor Jones gave in last week's lecture?
Exactly that. The agent can retrieve the exact textbook paragraphs and the snippets from the lecture transcript that detail that specific example. Then ChatGPT provides a clear, grounded explanation based solely on that retrieved material. This is a game changer for studying. It ensures the answers are perfectly aligned with the curriculum and the instructor's unique teaching style.
It turns hours of recorded lectures into searchable, structured knowledge. Amazing. Okay, our third example, the business knowledge agent, shows RAG addressing mission-critical internal operations, which is often the most complex and siloed documentation an organization has.
For this scenario, the source recommends Weaviate, mostly due to its scalability and good UI, integrated with existing business tools that people already use, like Zapier or Notion, and then feeding all of that into ChatGPT.
And what kind of data are we feeding into this corporate brain?
Everything. All the internal business data, standard operating procedures, SOPs, HR manuals, quarterly reports, client communication archives. You can even create a knowledge graph, maybe using Weaviate's Scratch capabilities, so the agent understands the complex relationships between these documents.
So it knows how a specific sales policy relates to the current refund procedure, for example,
Precise.
and the practical application for employees.
Yeah.
Let's imagine a really complex niche question a new employee might ask.
Okay. A new employee asks, I have a client in the APAC region who wants a customized bulk order. What are the exact stipulations and approval steps for initiating the bespoke manufacturing workflow, and who needs to sign off in the legal department?
I mean, that answer could be buried across 3 different manuals and 2 departmental
A
emails.
nightmare to find. A nightmare. The R agent retrieves the official internal documents from Weaviate, and ChatGPT replies using the exact policy-compliant multi-step language. It instantly operationalizes all that institutional knowledge. It makes every employee an expert on internal policy without them needing to navigate 20 different file servers.
It just eliminates the knowledge silo problem instantly. RAG is the critical bridge between all that raw, unstructured internal data and verifiable operational intelligence.
It connects data silos directly to the decision-making process with accuracy and speed. It's a huge unlock.
We've been focused so heavily on text, but as we've already seen with the educational agent, RAG is rapidly becoming multimodal. So let's look at how RAG extends beyond simple text to incorporate sight and sound, which greatly increases the agent's perceptual memory.
This is where RAG goes from being powerful to being truly transformative. I mean, if an agent is limited to text, it's ignoring 90% of the information we humans consume every single day.
Let's start with image RAG, or vision memory. What tools enable an agent to actually see and remember visual information?
Well, you need a stack of visual processing tools, something like OpenCV for manipulating the images, a robust text extraction tool like PaddleOCR for finding any text within the images, and then specialized vision embeddings. These are things derived from models like CLIP that can translate visual content, the texture, the composition, the object placement into vectors.
And what can an agent do once it has this vision memory? Can you give us a concrete example?
Sure. The agent can now integrate visual data right into its knowledge base. So imagine a quality control agent in a manufacturing plant. You could query it. Show me all historical cases where the serial plate attachment failed on this product line.
Wow.
The agent can retrieve not just the text of the maintenance reports, but also the visual data, the specific photos of the failed plates. It could analyze the location of the damage in the photos and even compare the signature on the original inspection document to a known list of authorized inspectors. It can essentially see and interpret visual evidence that's relevant to its knowledge base.
Okay, next up is audio RG. We've talked about meeting transcripts, but let's elaborate on the full scope of this for the modern workplace.
Audio RG, yeah, it relies on Whisper for accurate transcription, followed by embedding those transcripts. But beyond just summarizing meetings, the capability here is profound for governance and accountability.
How so?
It creates a searchable, queryable corporate record of every spoken commitment. You can ask the agent, what was the estimated timeline for the hardware deployment that was discussed in Monday's sync meeting? The agent retrieves the exact snippet of the audio transcript, confirms the commitment, identifies who said it, and can even link it to follow-up documents.
It turns unstructured, transient spoken conversation
Into a structured, searchable corporate memory. It saves countless hours of note-taking and ambiguity.
And finally, video RG. This is the most complex, right? It's blending both sight and sound over time.
It is. Video RAG requires a robust toolset, FFmpeg for precise video stream processing, CLIP embeddings for encoding the visual concepts in relation to text, and OpenCV again.
How does that translate into actionable knowledge for a user?
Think about complex training or maintenance procedures. Let's say you have a training library of videos that detail how to service a specialized server rack. An engineer could ask the agent, what torque setting is required for the second panel screw on the Model Z rack?
And the agent can find that specific moment in the video.
It can analyze the video frames, retrieve the specific visual insight, maybe a close-up of the technician using a torque wrench, confirm the setting from the accompanying audio track, and provide a precise, multimodal answer. It transforms dense video content into actionable, searchable, step-by-step knowledge.
It's clear that RAG is the operational framework for building agents that possess knowledge across all data types. But we have to address a critical point of confusion, one that comes up all the time for people new to this field. The difference between RAG and standard AI memory.
This distinction is so crucial for building a cohesive agent architecture. The source material draws a very clear line. Memory and RAG serve entirely different purposes, but they are complementary. They work together.
So how do we define standard AI memory in this context?
Memory, in the context of an AI agent, is short-term and personalized. It's what stores user preferences, the conversational history, what maintains the personality of the ongoing dialogue. It operates on a limited scale.
And critically, it doesn't store long documents.
Critically, memory does not store long documents or provide verifiable, knowledge-backed reasoning. It's the part of the agent that remembers the user is interested in history books and lives in London.
And RAG, by sharp contrast.
ORAG is the knowledge system. It stores long documents, gigabytes, terabytes, unlimited scale, and it provides robust, knowledge-backed reasoning that is traceable and auditable. It's used explicitly for domains like law, science, or internal company policy.
But it doesn't store user preferences.
It does not. It has no idea about the user's personal conversational style.
So if you want an agent that is both well-informed and personally attentive, you need both systems working together. RAG equals knowledge systems, memory equals personal preferences.
A fully intelligent agent needs both a vast library and a personal notebook. You need both.
We've built the system, we've picked the tools, but the quality of the grounded output relies so heavily on how we instruct the LLM once the chunks are retrieved. Let's dedicate some serious time to designing the RAG system prompt.
The prompt is the control mechanism. It's the thing that transforms the general LLM from this imaginative, sometimes flighty conversationalist into a restricted, verifiable expert. If your prompt is weak, the grounding will fail.
So what are the absolute mandatory constraints we must embed into that prompt to ensure high-quality, reliable output?
The single most important rule, the one you can't compromise on, is the core constraint. Use only the retrieved context to answer. This has to be the first line, the constant reminder. This one instruction prevents the model from injecting its general training data or from speculating. Any deviation from this just breaks the entire chain of accountability of the RAG system.
Okay, and what if the retrieval component fails? What if it doesn't find any relevant data? This is the safety feature, right?
Exactly. The second rule addresses safety and integrity. If no relevant context is found after the vector search, the agent must be instructed to say clearly and without apology, the provided documents do not contain this information. It must be forbidden from trying to guess or generalize or pull an answer from outside the knowledge base. This is accountability in action.
And then we also need rules for structure and citation to maintain that auditability we keep talking about.
Absolutely. The prompt must strictly instruct the agent to always cite its sources, document titles, sections, even page numbers if possible. And the answer itself should follow a clear, predictable structure. Usually you mandate something like a concise summary of the findings, followed by the specific references and citations, and then a final recommendation or conclusion that is derived only from that reference data.
This structured output ensures clarity, verifiability, and ultimately trustworthiness.
It's what makes the output professional grade.
Now, let's move to our final segment on high-quality mechanics.
Yeah.
The best practices for high-quality RAG. If a developer out there wants to get to 99% accuracy and reliability, they need to follow these principles meticulously. Let's start by just reiterating the absolute necessity of high-quality chunking.
We covered chunking earlier, but it really deserves emphasis here as a best practice. Overlapping chunks are non-negotiable for professional systems. If you're dealing with millions of documents, even small errors in context linkage, what we call context drift, will accumulate into massive accuracy problems down the line. A professional RAG pipeline includes rigorous testing to make sure the chunking strategy is appropriate for the data type, and that overlap is consistently and correctly applied.
The next point is vital for specialized fields, using domain-specific embeddings. Why is a general-purpose embedding model often not good enough when you're dealing with, say, financial or medical data?
Because general embeddings are trained to understand common language and context, but they struggle severely with specialized jargon. And that jargon is where all the important meaning is.
Give us an example.
Okay, think of the word motion. In general English, it means movement. But in a legal context, it means a formal application to a court. If you use a general embedding model on legal documents, and then you search for motion, it's going to prioritize the general meaning of movement. It'll return irrelevant documents about physics or physical movement instead of the specific legal filing you're looking for.
It just dilutes the signal. It doesn't understand the context.
Precisely. Domain-specific embeddings models that are trained exclusively on legal or medical or scientific texts, they understand the specific semantic nuance of that specialized vocabulary. They prioritize the context-critical jargon. And this results in vector representations that are infinitely more accurate when you're matching a specialized query to a specialized piece of knowledge. This one change is a critical factor in moving from, say, 70% to 95% retrieval accuracy.
Let's discuss something that often seems like tedious data engineering, but is crucial for performance. Removing noise from documents before you embed them.
This is probably the most skipped step, and it causes huge, huge problems. Noise is anything in the document that isn't core content but still gets converted into a vector, and by doing so, it distorts the meaning and actively reduces your search accuracy.
Can you give us a powerful example of how noise pollutes that vector space?
Sure. Imagine a 500-page internal company document where every single page has the same header and footer. Confidential draft Q4 2024 for internal use only. If you chunk that document without cleaning it, every single chunk now contains those high-frequency terms.
Okay.
So when a user queries, tell me about our Q4 2024 status, the vector search model sees those noise words in every single chunk and mistakenly believes every single chunk is equally relevant to the query about the draft status. It massively dilutes the semantic signal of the actual content you're looking for, though. One paragraph about the budget or the sales figures.
So the model can't distinguish between the structural text and the core content text. It all looks the same to it.
Exactly. Your pre-processing pipelines have to be robust enough to scrub out this noise. Headers, footers, page numbers, repeated boilerplate text, watermarks. Eliminated noise is a non-negotiable step for achieving top-tier retrieval accuracy.
And finally, the practice that dramatically improves both search relevance and system performance. Adding metadata.
Metadata provides context about the chunk, which goes beyond the actual words that are in the chunk. This metadata is stored right alongside the vector, and it's crucial for filtering the search space, which makes the retrieval process much more efficient and much more accurate.
How does metadata make the search more efficient?
It acts as a pre-filter. You don't want the agent searching through billions of vectors if you know the answer has to be in a specific category of document. Examples of essential metadata would be title, section, date, author, topic, document type.
So you can narrow the search field first.
Right. When a user queries the agent about a policy change, the agent can first filter its search to only documents that were written by the legal department within the last 6 months and tagged with the topic personnel policy. This narrows the scope exponentially before the expensive vector similarity search even begins, making the final result faster, more accurate, and much, much more relevant.
This detailed pre-processing really confirms that RAG success is, 80% sophisticated data engineering and preparation, and only 20% LLM instruction.
If the data pipeline is flawed, no amount of clever prompting or LLM instruction can save the output quality, garbage in, garbage out.
This brings us to our conclusion. Looking at everything we've covered, what is the transformative potential of these RI agents right now, today?
The potential is already being realized across nearly every knowledge-intensive industry. RAG agents are graduating into full-fledged professional roles. The source material summarizes them well. They are serving as legal researchers, academic scholars, HR assistants, processing company manuals, medical explainers, synthesizing treatment papers, and they're acting as robust, always-on enterprise help desks.
They're replacing these manual, hour-long research tasks with instant, verifiable insights.
That's the core value.
And the most important takeaway for anyone listening is that this power, this ability to custom build your own grounded intelligence, is accessible.
Absolutely. You can build highly reliable, knowledge-driven agents using these accessible, often completely free tools like FAIs, Chroma, PaddleOCR, Whisper, and OpenCV. The architecture has matured to a point where bespoke, verifiable intelligence is within reach of any organization or any motivated developer.
Before we wrap up, let's offer the listener a quick pre-deployment checklist, the final RGRED checklist, to make sure they haven't missed any critical steps in their build.
Good idea. Before launching any RAG system into production, you have to verify this final checklist. First, verify the chunks were created with proper overlap and the right size. Second, ensure the embeddings were successfully generated, ideally using those domain-specific models. Third, confirm the vector database is correctly configured and populated, paying attention to all your necessary metadata fields.
Okay.
Fourth, test that the retrieval mechanism is working and returning relevant low-noise chunks. Fifth, ensure the prompt is strictly aligned with your grounding rules, including that use only this context constraint. Sixth, verify that all your safety rules, like the never guess rule, are added and enforced. And finally, if it's applicable, confirm that your multimodal support, your OCR, your Whisper, etc., is integrated and functional.
That is a comprehensive operational summary of the entire journey from raw data to grounded intelligence.
You know, what stands out when you look at that checklist is the sheer amount of effort that's dedicated to cleaning and structuring the input, specifically those crucial steps of removing noise and adding rich metadata.
That reliance on curated input, it raises a really fascinating question about the future of work, doesn't it? We've established that removing noise and adding rich metadata drastically improve the accuracy and the efficiency of these systems.
Which leads to an important question for you to consider as you build your own knowledge systems. If removing all that low-value noise and adding rich, human-curated metadata is paramount to retrieval accuracy, what does this tell you about the future of knowledge systems? Specifically, how crucial will human curators and specialized knowledge engineers become in preparing, tagging, and maintaining data purity for these massive, reliable ARG engines to function effectively at an enterprise scale?
The AI needs knowledge, but it needs clean, verified, and tagged knowledge.
Exactly. The era of the human data curator, the person who makes the data RG ready, might just be starting.
A truly provocative thought. Thank you for joining us on this deep dive into retrieval-augmented generation. We look forward to seeing what reliable, grounded intelligence you build next.